So that's what this section's Ohm's law. Ohm's law states that the voltage across conducting material is directly proportional to the current flowing through the material. Directly proportional. In math, we got direct variation, V equals R times I. And that constant R happens to be the resistance. So that's really what Ohm's law, V equals R times I. So I just want to put that in. Let me just here. So the power or voltage, that's Ohm's law, equals I times R. Is directly proportional, meaning what? If you take a resistor, this is a picture of a resistor, let's say if 10 ohms, and you take that and you apply a voltage source here to it, let's say 5 volts. This is going to force a current to travel through that, through the source. Since the source supplying the power, the current will travel this way. That's what I is. It's going to travel around like this. So the current, will say voltage is 5 equals I times R. R is 10. So if you do the math, I equals to what? 0.5. Now if you take the same resistor and instead of putting 5 volts, you put in 10 volts here. Current's going to travel this way. Again, I. The current for that will be Ohm's law says V equals I times R. V is 10. I is unknown. We're looking for it times the resistor, which is 10. I equals 1 amp. So notice you increase the voltage, you get a bigger current. You lower the voltage, you get a lower current. That's what direct variation. When one increases, the other one increases. When one decreases, the other one decreases. It says the voltage and the currents are directly proportional. So if you actually increase the voltage, the current will increase. If you decrease the voltage, the current will decrease, and vice versa. If you increase the current, the voltage will increase. Decrease the current, the voltage will decrease. That's what Ohm's law. Now, if you take Ohm's law with power and put them together, we can create Coulomb equations for power. So power, okay. Put that under. We know power equals V times I. And if I use Ohm's law, instead of V, I'll put I times R for the voltage, multiplied by I. You also end up with power being what? I squared times R. So this is one of them. This is another one, I squared times R. And a third one, again, we can derive a third one. Power is V times I. Going back to Ohm's law, V equals what? I times R. So what is I equal to? V over R. So if you do that substitution, plug it right here. V times, in place of I, we'll put V over R. You end up with what? V squared over R. So 3 ways to calculate power. So power, P, is equal V times I, or I squared times R, or V squared over R. You can use any one of them. It depends what's given to you in the problem. And again, power can either be absorbed or supplied. If the sign for the power, we said that last time, if the sign of the power is positive, for us, positive means what? Absorb. If the sign of the power is negative, power is what? Supplied. So let's go back to that example I just did here. We calculated the current to be 0.5. And let's see what happens. The marker bleeds through. So we have a voltage source of 5 volts. Same one I just did before. Just instead of sideways, I turned it up and down. And this is the 10 ohm resistor. The current is going to travel this way.
That's 5 volts, right?
5 volts, yes. So the current using Ohm's law, again, V equals I times R. V equals I times 10. What's I equal to? 0.5 amps. So this current is going to come down through that resistor. Resistor is not charged yet. As the current goes through it, it's going to mark the resistor plus to minus. When the current enters that resistor, it's going to mark it. Current always travels from where? Just like water. You pour water, it's going to travel from top of the hill, the high, to the low. Current the same way. Is the current going down this way, it's going to mark it plus to minus. That's the high, that's the low. If the current going up there, it's going to be this is the high here and there's the low there. So let's look at the power for this. We have a current entering the negative end. That's the remember, that's plus voltage, that's a negative voltage here. That's a source. I have no control over it. I have a positive current entering that node, that negative, the minus sign. So the power for that 5 volt source is going to be minus because it's being supplied. If a current enters the negative, we said that's negative. If the current entering the positive, that's positive. So it's going to be V times I. And V is what? That's the negative. What's V? 5 volts. And what's I? 0.5. And we have negative 2.5 watts. This source supplied 2.5 watts. So the 5 volt source supplied, because of the minus sign, 2.5 watts.
Now why is it minus again? I mean, why is it a negative?
Let's go back here. Question, why is it minus? When the current arrow is directed into the element at the plus marked terminal, we satisfy the passive sign convention. What does that mean? In other words, it says that if the current arrow and the voltage polarity signs are placed such that the current enters the element marked with the positive sign, then the power is absorbed by the element.
So if the current goes like as in this counter or no clockwise,
yep,
it's going into the positive part.
It's going to positive side of the resistor, not the source. It's going this way. That's entering the negative.
So if the current was the other way, it'd be positive.
Correct. If the current was going this way, that'll be a plus, which means taking it. If you only have one source, the source is not going to absorb power, it's going to supply it. If you have more than one source, one could absorb, one could supply. Yeah.
Okay.
So that's why you have a positive, the arrow of the current, the direction of the current, the head of it is entering the negative. That's why it's supplied. For this one, the arrow or the pointer of the current's entering which one? The plus end of that resistor.
Of that resistor.
So that'll be a plus. That's absorbed there. So the power absorbed
It's absorbed in the resistor.
and supplied by the
supplied
source.
by-
Yep.
Okay.
So the power by the
Gotcha.
10 ohm resistor is going to be, you have the arrow, the tip of the current entering the plus, that's positive, V times I. It's positive. Again, the voltage here is the same voltage here, it's 5 volts. And I for that is what? 0.5. Or if you don't want to use that equation, that's positive 2.5. You go, well, I don't know if the voltage is really 5 here. I know the voltage here is 5. I say, okay, got you. I understand your concern. Use the other equation. I squared times R. What's I?
I 0.5.
0.5 squared times R, which is what? 10. What's 0.5 when you square it? 0.25 times 10.
2.5.
So any way you slice it, it is plus 2.5. So the power by the 10 ohm resistor is going to be absorbed 2.5 watts. This guy supplies 2.5 watts. This one takes 2.5 watts. What do we have? Conservation. Whatever is being supplied is actually equal whatever being taken. We have conservation of energy.
So, whenever like you're hooking up like electronics to like a circuit and stuff, it has to have a resistor in order to get absorb energy from the circuit.
No, I can have another source. I can have two sources. One force the other one to absorb power. You know?
Capacitor, right?
Yep. I can have other. Yeah, I can have other elements there.
But if you just have a straight piece of wire, then you short the battery and it can't.
Correct. If you put a wire across this, that battery's gone. Then we got a problem. That voltage source now you force it to be 0. And if you try that actually, if you take a battery and you put a wire across it, within about a second while you're holding the wire in place, you will go, ouch! It will burn your hand. It will get really hot. And you can try that with just one battery, 1.5 volts. You will actually scream and throw it away. You go, ouch! Within less than about 30 seconds.
And sometimes in robotics, we had 9-volt batteries for our, they were like a backup battery for a robot. And every once in a while, we check it. And the quick way we would check it,
On your
we'd
tongue?
take it and you put it on your tongue.
Yep.
So
Yeah.
gross, but
Yep.
like when you're in the heat of the moment,
Yeah.
you're up in 10 seconds, you got no time at all, and
Yeah, not a pleasant feeling.
no, but it's worth it. It saved us a couple times. Because if it's not on there, your robot